call the trail T. So we have a circuit, I guess. If G is an Euler circuit, then there's something that starts at some particular vertex, and it just goes like V1, V2, and it eventually uses up every vertex. Okay, well, and it might visit vertices multiple times. Well, why can I say for sure that there are no vertices of odd degree? Oh, sorry, this is like crap. The whole point is that we're supposed to end at back again if it's an Euler circuit. Whew. Everyone feels a little dead today. Are we awake and alive? Yeah, good. Fake it and then you'll feel alive in a couple minutes. All right, good. Woo. Suppose G has an Euler circuit. So you have a graph. There is a way around the graph following all the vertices. I guess this is like a little bit of bad notation because this is a multi-graph. So this is a little bit bad for us to just list the vertices. Really, we should list like the edges. Maybe we don't even need this sort of formalism. Maybe we can just do it. Let's see what the Evan's got. Evan.
Oh, well, I was going to use what you had written up.
Well, then can I make it a little bit better? Which is, like, it's like V1, like E1, V2, E2, etc. Right? Because it is possible that there are multiple edges between vertices. So we really should sort of have something like that, etc., etc., etc. And then eventually we have some edge. Who knows how many edges this graph has? But eventually we get back again. And we end back at V1. Okay.
So like every vertex is adjacent to two edges. I don't know. It just like kind of does it. Like every time it appears, it's adjacent to two edges. So it just can't be off.
Yeah. I mean that's pretty much it, right? This is going to use up every single edge in the entire graph exactly once. So every edge appears. But in this list of the particular vertices and edges that are used up in this circuit, when every edge appears, as every edge appears, it just like subtracts exactly, well, I think I'm saying it wrong. Let me try to say it right. Every
time a vertex appears.
Let me add in like an extra little VI type situation, and then we end back at V1. So for every vertex that appears in the middle,
there's an edge on either side.
There's an edge on either side, and that edge on either side removes 2 from the degree of that vertex.
Or adds 2. I don't know about, I would go with
every vertex has two, and every time a vertex appears, it has 2 edges
unless it's
with it.
Yeah.
2 different edges, and you know that because you said that C is an Euler circuit, you know that there can't be any other edges that aren't listed in this swap.
Like 2 new different edges.
That aren't right, because it's an Euler circuit.
Yeah, since we use every edge, the degree of every vertex can be just counted by the number of edges that appear adjacent to it in this list, right? And we use up 1 degree going into that vertex and 1 degree going out. And the only special case is like the first one, right? But then we use 1 at the start and 1 at the end, so it's pretty much it. Far more difficult, I think, is going in the other direction. The other direction says, suppose that G has no vertices of odd degree. And from this, from the fact that G has no vertices of odd degree, what we want to do is prove that G has an Euler circuit. Oh, and I guess I need that's like connected and stuff like that. I'm gonna add that in a second. Okay. So, who has some thoughts? So we do like just a quick example to like kind of get us sort of like worked up or whatever. So let's do it. Let's just make kind of arbitrary. I'm gonna draw a picture and then I'm just gonna like erase it. And I'll sort of outline Gossett's like proof, which is like, you know, somewhere between acceptable and good or bad. Okay, let me just try to draw some graph with all even vertices. I don't know how hard is this to do. Maybe kind of hard. Maybe not hard.
You need another one of that central.
A few others.
Really? No, this one is 5. Oh, okay, done. Okay, great. Beautiful graph. Fact, all vertices have even degree. So according to this theorem, G should have an Euler circuit. Okay, how can we make an Euler circuit? All right, well, it's just like, you know, we can just start and just kind of go and just do it and it'll work, right? And just use up every edge. It's actually not that hard to see. But why should I expect this to always happen? Give me some sort of algorithm, I guess, for constructing an Euler circuit. So we need to start at a certain place and end back at that same place and use every edge exactly once. All right, well, one thing you could think is, this is Gossett's proof. He says, look, start somewhere. Doesn't matter where, because the very nature of the algorithm is you don't have a global picture. You're not doing anything, you know, creative. You're just following along mindlessly. All right, so start somewhere, right? And now, just like go, man. This is Gossett's proof. So like, just like go, use up that one, and you get somewhere, use up that one. And oh, by the way, you're never going to get stuck this direction to just go. You're never going to get stuck. Why are you never going to get stuck? Because all of your vertices have even degree. So every time you go in and back out again, you're using up precisely 2 degrees from that vertex. And so you're never going to get stuck at a vertex because you're always allowed, if you go in, you're always allowed to go back out again because, follow? Okay, and now, what's one thing that might happen? Oh, so then this is the other thing that Gossett said. If you just keep going eventually, you will end up back where you started. Why?
Because you left it, so you have to use one of the, it's connected to the edges.
So it's connected is key, right? So since it's connected, that's relevant. And also, you're never going to get stuck. And also, the graph is finite. So if the graph is finite, and you can't get stuck, and it's connected, there's only one possible thing that can happen, which is that you're going to end up back where you started. Because like, there's no way to not end up back where you started, because you can't get stuck anywhere. Who buys that?
You can get stuck if you go where you started, but way too early.
You can get stuck. Oh, so yeah. So notice that Alana says you don't necessarily finish constructing. In fact, that's what I'm going to do right now, right? Suppose I start here, because I'm just, so mindlessly follow just vertices, and do that until you end up stuck again. Oops, I'm not stuck, but I have completed I've completed a circuit, but it's not an Euler circuit. Follow? Okay, so now do you have a recommendation?
Send out 2
So
probes.
I should probably like label this. It's like V1, V2, V3, V4. Send out another probe.
Send out like 2 probes at once, and then every time you get to like a split.
I don't even think it's that. I don't even think it's that complicated.
Start again from the
Yeah.
that was like a sci-fi reference or something.
Leave what you have, but now here. So now okay. 2 things can happen, right? If you just started this is Gossett's proof. Started an arbitrary vertex. Just go. You end up going and going and going. You can't get stuck. 2 things can happen. You end up back at V1 having just by accident used every single edge and you completed the Euler circuit. Or you ended up back at V1, but there are unused edges. Agreed? Now, this is where the argument gets very convoluted. Some years I've convinced the class, other years not. I think it just is a bad argument. But like, somewhere, if there are edges left to be used, where are those edges? Well, they have to be connected to at least one vertex on the path that you have completed so far. Because somehow they can't not be, because if all of the edges that were unused, if there were a bunch of unused edges, but that none of them were connected to this initial circuit, then it would be disconnected. It would be in its own component, right? Or something like that, right? So therefore, there must be. Not only must there be, if there are edges unused, then there must be edges unused which are directly incident with vertices on the path that you completed in round 1. That's plausible, but not airtight, in my opinion. So then, of course, what you do is you just go to one of those vertices, and then just like repeat the step again, right? And so now do like a zoom, 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 and again, what could possibly happen is, well, the only thing, you could finish the whole thing, or, as happens here, you could end back again. Well now, what's up? 4.5. Good. So now you get back here again. Okay, well now just repeat the algorithm, right? If you use all the edges, great. If you didn't, then use another, then use 7, 8, then use another point on what's been completed so far, which may be on either one of these, right? You sort of patch this now together, and that I should say. At each stage, you sort of patch the route together, like via V3. You think of V3 as like a detour point, follow? And then in this case, it happens to be the same detour point. And so therefore, we've constructed the Euler circle. It goes like this. It's V1. Well, the algorithm, I guess, goes like this. You do V1, V2, V3, V4. I guess this is sort of a bad example because it's not a multigraph, but anyway, who cares? Then back to V1. Did I use every edge? Oops, no I didn't. So I stick in between V3 and V4, I go on a V5, V6 detour, follow? And then I like also V5, V6, V3, I guess I should say, yup. And then that also didn't work, so now in between V3 and V4, I like stick in another V7, V8, V3. And so the full path becomes V1, V2, V3, V5, V6, V3, V7, V8, V3, V4, V1. Cool? Alright, I made that a little bit easier on myself because this is just a what's it called? Simple graph, yeah. Woo! Okay, so that's like kind of a baby proof, I think. When this is one of those proofs where like if you're willing to take it kind of casual, it's really easy. But then if you want to make it rigorous, suddenly you're like, oh my god, I have no idea how to do this. I've definitely had years where I was teaching discrete math and like we spent like a half an hour trying to like tighten up this proof. Well, any sort of kind of note that the algorithm is like sort of recursive, like in nature, right? Which suggests that the best way to do this, if we want sort of like a rigorous argument, is to do it by induction. Woo! So that is what we'll do. Let's go. Induct on the number of edges. Oh, stay awake. This is actually kind of cool, I think. Induct on the number of edges. Alright, well, what's the base case? How many edges are there? What's the simplest possible connected graph? Yeah, like 2, right? Yeah. So, base case. Connected, or you guys are saying 2, but I think we really mean like what? Oh no, it has to be, in order to have even degree, it has to be a graph with 2 edges and 2 vertices, yeah. So base case is a connected graph with 2 vertices and 2 edges. Or I guess I don't even need
vertices, which is bad. Yeah, because you could have.
Hold on, I gotta think for a second. 2 vertices. Yeah, I think that just is the base case, right? Because there's no simpler graph. Our assumption is that this is a graph like It's not like the empty graph. That's like not a graph in our world, right? It has to have at least some vertices and some edges. So I can't have a graph with one edge that meets the conditions of the theorem because there have to be.
Yeah, you can. Single vertex loop. That counts into multi-graph.
Single vertex with one edge.
That's good.
Okay, there are two base cases. There's this one, there's this one, and this one. Do we all agree that in both of these in both of these base cases, these are both graphs with that satisfy the conditions of the theorem. There are no vertices of odd degree, and there just are. It just is an Euler circuit in each case. Cool. Say cool. Cool. Woo! Okay. So now inductive hypothesis. Inductive hypothesis. Suppose we have a graph G with m greater than 2 edges. So maybe I should write this. So the inductive hypothesis is that, I guess we're doing strong induction even. Should have like written this all down. Okay, good. Inductive, we're doing strong induction. So suppose that every connected multigraph with less than or equal to m edges has a Euler circuit. Suppose that every connected multigraph with less than or equal to m edges has or every connected multigraph with vertices with all vertices of even degree and less than or equal to m edges has an Euler circuit.
Oh, yeah.
This proof by this person is so casual. Okay, so yeah, now we are going to show it for m plus 1, right? Okay, so this is my inductive hypothesis. I'm doing strong induction. I'm inducting on the number of edges. So suppose that all graphs with below a certain number of edges work. This actually,
Wait.
yo.
So this assumes that you can form a graph with all even degree vertices with any number of edges.
No, I don't think it does. I think the theorem is that if you have a graph where all the vertices are,
Because you're trying to prove for m plus 1.
yeah, so wait, what's the problem?
No, it's an if statement, so we're fine. It's like for all connected multigraphs with m edges and vertices of all even degree, blah blah blah. And so if there is no, then it's back to zero, right? It's no big deal.
Oh, yes,
yeah,
yes,
okay.
yes, yes.
Also, like, if it's a multigraph, you can just add a self loop. Like, there's not a problem there.
Okay, wait, hold on. Let's keep going. Suppose that every connected multigraph with all vertices of even degree and less than or equal to m edges has an Euler circuit. So what we want to do is let G be a multigraph with m plus 1 edges, and all vertices of even degree. And what we want to do is to show that G has an Euler circuit. Cool? Say cool. Okay, here's what you do. It's like beautiful. Well, yeah. You start somewhere. Arbitrarily start at a vertex B in G. And begin going on a walk at random, as we outlined earlier. What is going to happen? well, you're going to keep on going, and you're eventually going to get back to V again, for all the reasons that we just said. Every time we encounter a vertex other than V, we are going in and back out again. We can never get stuck, and so this process will always lead us back to V. So we have some walk, kind of does this, and let's just say, yeah, cha, cha. Okay, so and I'll introduce some like dot 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 thing. So let's call this. Let's suppose. So let's call this walk. Call this walk W, or I guess it's a trail. Well, I don't know. I'll still call it W. Every trail is a walk. And suppose that W has precisely. Well, never mind that. What the hell is going on? Oh, okay. So, all right, here we go. This is V. And then we have a vertex, a vertex, a vertex, a vertex, a vertex. All right. So now, what happened? Now consider the following graph. Consider the graph. Let this graph G be, like a set of vertices and a set of edges, like as usual. Now consider the graph, which is G minus the set of edges of this graph. I don't like this notation. I should have written this myself. I can do it, I think. Just like kind of put this piece of paper down. Call this walk W. So now consider the graph G minus W. This might be a mild abuse of notation, but what I'm trying to say is take the graph in which we've removed all the edges of this walk W. All right.
Yeah.
Okay. So now what do we have?
Maybe connected graph.
A maybe connected graph, right? But it might not be connected. Because what this graph might look like is, wait, why is it maybe connected?
Because you could have a loop off one and a loop off another.
Yeah,
And then maybe removed, sure. Yeah, and like in general, that is what it's going to look like, right? So cha, 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 or like whatever. Okay, so like if this is like V1, and this is V2, and this is V3, V4, V5, etc. Okay, so what happens is your graph might be connected, but it might be broken up into a whole bunch of different components. Because when I remove these edges, I now disconnect the rest of that graph that's up there, right?
And if say V5 only had 2 edges on it in the first place, then it would also be a floating point.
Say again?
If V5 only ever had those 2 edges, then it would now have no edges.
Then it would now have no edges. Yeah, sure. Okay, so in general, when I have this this graph, which I get from removing all these, I'll sort of just like I'll draw the edges in red if they've been like removed, right? And so only like the black edges remain in this new graph, right? And so in general, this will be disconnected. But it will be disconnected up into components. And what can I say about all these components? Yeah, well...
We need to predict all the even number of edges first.
Yeah, so consider each component. Consider each component like C sub I or whatever. Well, yeah. What can I say about the VI? Here, I'll make this like VI. So we're going to do this now like in general, right? So this is component CI. This is VI. But of course, when I passed through VI, I used precisely 2 degrees of it, right? And on the assumption that VI had even degree, I've subtracted 2 from the degree of VI. So for every vertex visited on this path, it like still has degree 2 because I used 2 degrees when I made this initial walk.
You actually could have used any even number of degrees on your
Yeah, because it's possible that I visited a vertex multiple times in this walk. That's true, right? But so if I consider each component now, well then just like all the vertices still have even degree. All vertices in CI still have even degree because in the preceding, well, because in this walk I removed only an even number of edges, or I removed an even number of degrees from each vertex, because when I went in and out, I just took 2 edges away. Okay, and so now more to the point, also each of these components has like less than m edges, right? Also, each component has less than or equal to m edges. And so by induction, there is an Euler circuit on each of these components. And now you just patch them together. In exactly the way we said, right? So just start at V. This is really the whole proof, right? You just start at V. You go to V1. Look, the original graph is connected. So any component in G minus W is going to be touching one vertex along this path of this walk W, because otherwise it would be disconnected. So since this graph is connected, wherever this component that got disconnected by removing these red edges connected to the original walk, we'll now just sort of loop it in and now do the Euler circuit that starts at that vertex of connection and then goes around and that's it, right? And so, like, look, here are the various things that can happen. I mean, you basically are just this is the big idea. This is a shitty presentation, but the basic idea of this proof is, look, if you just assume it's true by induction for all graphs of with a certain number of edges, then just go on this random walk. You go back to V. Like we said before, either you just get lucky and you use every edge, in which case you're done because you can never get stuck, or you have some unused edges. But now, unlike before, in which there's some sort of algorithm for what to do with those unused edges, now we simply, it's very similar, but now we simply invoke induction to say, well, what remains is, there are 2 cases. Either it's a connected graph with fewer edges, in which case by induction we automatically get that there's an Euler circuit, and then we just put the 2 together. Or, if the graph is broken up into disconnected components, each of those disconnected components still has even degree, is touching my walk in some kind of way, and it's subject to the inductive hypothesis, and so we just patch it all together. I feel like that's good enough. Cool? Okay. What's up?
We're just talking about another algorithm.
Oh. Good. Wait, the final thing is, it's usually best to say the theorem this way by proving this theorem about Euler circuits. But what about Euler trails? When am I going to have an Euler trail?
There are less than 3 vertices with off degree.
Yeah, I think specifically it's when there are exactly 2.
Yeah.
Okay, so remember how last class we proved that you can't...
2 or 0. Right?
2 or 0, yeah, right. Right, so last class we proved that... well, no, I guess if it's no, I guess if it has 0...
Well, then it's an Euler circuit, but an Euler circuit is also an Euler trail, right?
Sure, okay, sure. So I'll have an Euler trail if there... Is that how he phrased it? 2 or 0? That's kind of weird. But I guess that's right. It must be. I feel like there's a smoother way of saying it. Okay, he just said an Euler trail, but not an Euler circuit. So Euler trail, but no Euler circuit, if and only if there are exactly 2 vertices of odd degree. And the theorem goes like this. Suppose first that there is an Euler trail but no Euler circuit. Why are there exactly two vertices of odd degree? No, I guess it's the other way is better. Suppose there are, what the hell?
What are you doing?
He's taking a picture.
Who's taking a picture of him? No.
The board, but I'm standing in the way. Let's just do this out. We're going to use the widths of the class. Why must there be exactly two vertices of odd degree if there's an Euler trail but no Euler circuit?
Well, there can't be zero unless there's no Euler circuit.
No, but let's do the forward direction first. So, oh no, that's what I have to show, that there are exactly two of odd degree. So here's somewhere where I start, and I go on and on and on and on, and I eventually end somewhere else, right? Well, every vertex must have, if I've used every single edge, then every internal vertex must have, this is just trivial, right? Every internal vertex must have even degree, but also the first vertex must have odd degree because I start here, I use 1 degree going out, and I use 1 degree ending. Yo.
If you connect the two vertices that have odd degree, then you've got an Euler circuit.
Yeah, I think that's how we do the other direction, right? To do the other direction, but you're exactly right. To do the other direction, why? Suppose that this is what I have. Suppose I have one vertex, V1 of odd degree, and suppose I have some other vertex, Vn, which is also of odd degree. And now suppose that every other vertex has even degree, okay? What I would like to claim is that there is an Euler trail but no Euler circuit. Well, there just is, because what I'm going to do is temporarily add an edge between V1 and Vn. And if I add an edge between V1 and Vn, now I have a graph in which every vertex has even degree. And if I have every vertex has even degree, now there just is an Euler trail. Circuit. And then just kind of like remove that again, and then that shows there is your trail. Just start here and end here. Wait, is it really this? Is this the correct time? There's 20 minutes left in this class?
Yeah.
Oh my god. Okay, good. That was one of my worst ever presentations, but we're gonna rebound. Are you ready to rebound?
Yeah.
Woo! There's a whole, this is one of the central questions in graph theory which we've settled in a non-entertaining and non-efficient manner. The existence of Euler circuits. And there's this nice, happy fact, which is you get their existence based on just the degree of the vertices. Okay, but there's another kind of question. The sort of other question is, can I have a graph where I visit every vertex once? And let's